dear students, today we are going to discuss about relation and mapping. Now, before going to start relation, we have to know one more thing. What is Cartesian product of two sets? Now, if A and B are two non-empty sets, A not equal to 5 and B is another set that is also not equal to 5. Now, if we collect all the pairs of from the set A and B, that is A cross B, we can write in this way: the collection of all pair, not ordered pair, where A belongs to first set and small b belongs to this set. Suppose uh, if we take, as for example, if you take A as 1 2, A as 1 2, and B you can take as suppose A and B, then can you tell me what will be A cross B? Then if we calculate A cross B, then the pair A comma B type, and that will come, the first component will be from first set and second one from second set. So it will be 1 comma A and then 1B, then 2A and 2B. Now if we take any subset of A cross B, then that is a relation from set A to set B. Now what is subset? Subset means anything, whatever you will take from that A cross B. Here total number of elements in A cross B is here is 4, so we will get 2 to the power 4 subsets, and each subset is a relation from A to B. Just see here. Now this one suppose our 1 2, and this one our A and B, this our set A, this one set B. Now for that A cross B, if we take, suppose R1 is a subset of A cross B, R1 subset A cross B, and R1 we are taking in this way, where R1 is equal to, from that A cross B we can take, suppose we are taking 1A and 1B, 1A and 1B. Then how does this relation look like? This one tells us that the first element of A set is connected with first one of this one, and second one is connected with B. So this is exactly the relation R1. Now this way we can define so many relations. Here, since if a set A, the cardinality or number of elements in a finite set may be M, and if B contains n elements, then the number of elements in A cross B will be Mn, and then total number of subset will be, as you know, 2 power Mn. That means 2 to the power Mn numbers of relation we can define from set A to set B. Now there are different type of relation also. Now we are going to discuss about those. What are those different type of relations? Right. This one. Okay. First one is reflexive relation. Reflexive. Now, if this relation tells us, if for all, suppose A and B two sets, and R is a relation from A to B, that means R is a subset of A cross B. Now, if for all A belongs to A, capital A, if we see that A cross A belongs to R, and this holds for all A belongs to A, then we can say this relation is reflexive. As for the previous one, or if we take a new example, suppose A and B both are our same set. A and B both are same set. A is equal to B is equal to 1. Then clearly here in A cross B, the elements will be 1 comma 1, 1 comma 2, 2 comma 1 and 2 comma 2. Then if we want to define a reflexive relation, then that relation must contain the element of same type. Same type means A comma A. That means 1 comma 1 should be there since 1 belongs to A. So if we want to define a or give an example of a reflexive relation, suppose this one R1, then our R1 will be 1 comma 1, 1 comma 1, that should contain 1 comma 1 and 2 comma 2. Also some extra element can be there. Okay, and if no other extra element be there, then we say this is an identity relation also, sometimes we say. Now there are another kind of relation, that is called symmetric relation. In case of symmetric relation, there should be the inverse element should also be there on that relation. If A comma B belongs to R, then B comma A should also belongs to R. If this holds for all such pairs in the relation, then we say that is symmetric relation. Just see here. Just see here what is symmetric relation. Suppose R be any relation. Relation means that is obviously a subset of A cross B. Now if whatever the elements are contains, suppose those elements are in AB type, then if AB belongs to that relation, implies BA also belongs to that relation, and this holds for every pair of such elements. Every pair of elements belongs to that relation. If this holds for all such pair, if this holds for all pairs, in R, then we say this relation is a symmetric relation. For example, we can take, suppose A is our 1, 2, 3 and B is also same set 1, 2, 3. Now a relation R, if we define this one, suppose R2. Now if we define R2 in the way that is, suppose 1, 1 is here, 1, 2 is here. So can you tell me, can we say this one is symmetric in this case? If I write R2 up to this, then the inverse of 1, 1 is 1, 1. No problem, it is here. But inverse of 1, 2 is not here. Up to this, we cannot say this is symmetric. So to be symmetric, we must have 2, 1 in this set. Up to this one, we can say this one symmetric relation. Now again, if we want to add some other element, suppose 2, 3, then obviously 3, 2 also we have to add. Now this one we can say this is a symmetric relation. In this way, we can define symmetric relation. Now there is another kind of relation, that is called transitive relation. Just see here what is transitive relation. Transitive relation, for this one you have to take two pairs of elements. Suppose RB relation. Now if x, y, or you can take, previously we took A comma B, so we can take A comma B. If A comma B belongs to R and B comma C belongs to R, and together both, this implies A comma C belongs to R. And if this holds for every such pair means what will be the ending element, ending component here in the first one, and in the second pair that should be the starting one, and then at the final you have to get first one and the second one of the second pair. And if this holds for every pair of every such pair of elements in R, then we say this transitive relation. Okay. Now, for example, if we take R3, suppose I am telling you 1 2 is here, 2 1 is here. So to be transitive, 1 2 is here, 2 1 is here. So we must have to be 1 comma 1 there in this set. Now we have to check this one for all such elements. Now starting from 1 there is no problem. But now again we have to check the element from the second component, second one. Now for second element, if we take this one A, this one B, then again starting element one you will get here also and here also. Now for the first one, 2 1 and 1 2, 2 2 must have to be there. So this one we can say this one is a transitive relation, and for this one, for 1 1 2 2 3 3 type elements, we don't need to check because this will provide again that one only. 2 1 and 1 1 you will get again 2 1, so automatically this one hold. So this R3 is a transitive relation. Now there are another one relation that is called antisymmetric relation. Antisymmetric relation is this one. Antisymmetric relation. Now if AB belongs to R and BA belongs to R, AB belongs to R and BA belongs to R, BA belongs to R, AB belongs to R and BA belongs to R, if together these two implies A is equal to B. If this implies, then we say this is antisymmetric. Antisymmetric does not imply not symmetric. Okay, there may be relation not symmetric, not antisymmetric. Okay, now just look here. If a relation both be reflexive, all of these three, suppose reflexive, that one symmetric and transitive. Reflexive, symmetric and transitive. A relation holds all these three, then that relation we call equivalence relation. Then that relation we say equivalence relation. And again, if a relation be reflexive, antisymmetric, reflexive, antisymmetric and transitive, then that relation is called a partial ordered relation. A partial ordered relation. A partial ordered relation. Okay, now we are going to start. What is the time now? 15 minutes. 15 minutes. Okay, now we are going to start what is mapping and what is the relation between relation and mapping. What is mapping or function? Okay, suppose we are taking some relation. Suppose our A and B both are these sets 1, 2, 3, and B is also 1, 2, 3. Now this is our 1, this is 2, this is 3. Here is also 1, 2, 3. This one 3 elements, and here this one these 3 elements. Now this 1 goes to 1 means 1 is called the image of 1, and 2, suppose we are sending 2 to 2, and 3 is empty, 3 is going to nowhere. Then another one we are taking this way, 1, 2, 3. Here is also 1, 2, 3. Suppose we are sending 1 to 1, 1 to 2, and then 2 to 3. Okay. And last one, another one. If we take 1, 2, 3 here, 1, 2, 3 here. Suppose this one, this one, this one. Or first one we can take this one also. Now, if we take A and B both as 1, 2, 3. This is our A set. This is our B set. This is A. This is B. This is A. This is B. Okay. Now, this 1, 2, 3, and obviously, if we want to write this one as a relation, what we will get as a relation? We can say first one, suppose R1 set. Then R1 we will get is 1 is connected with 1. 1 of the first element, first set, is connected with the 1 of second set. That means 1 is connected to 1, 2 is connected to 2, and 3 is connected to 3. Similarly, this one be R2. Then you can write what will be R2. Clearly, you can write this one. This will be 1, 1, 1, 2, and 2, 3. And also R3 also, last one R3 also you can write this way. That will be 1, 2, 2, 2, and 3, 3. Now, our mapping is a special type of relation in which every element of the domain set should have unique image in the codomain set. Codomain means second set we say codomain, and first one is domain set. If that be mapping, every element of the first set should have unique image in the second set. Now, there are two conditions actually. If a relation satisfies this condition, first one is every element should have image, and second one is image should be unique. This two. Now, if we come to the first one, then we can see here 1, 2, 3. All the three elements are have images. All these three elements have image. Image of 1 is 1, 2 is 2, and image of 3 is 3. So, this relation we can say this R1 is a mapping. Now, if we come to this one, here you can see the first element 1 have two images. 1 goes to 1 and 1 goes to 2. That means one is the image of 1, also 2 is the image of 1. So, since 1 have two images, that means image is not unique. So, we can say this is not a mapping. And now, third one, can you guess what can be the third one? Third one can be mapping or not? Here, how many? First, you have to check two conditions. First one is every element should have image. 1, 2, 3, all are connected with the elements of B. So, no problem. Every element have images, or each element of capital A have images in B. Now, images are unique or not? This element 1, how many images this have? Only 1. 2, only 1 image. 3, only 1 image. So that means both the conditions, these two holds. So we can say this is also a mapping. Now, there are different type of mappings also. 1, 1, 1, 2, or 1, 1, 1, 2. That is called bijective. Then some mapping may not be 1, 1. That is called many 1. Some mapping may not be 1, 2, that is called into mapping. In the next class, we will discuss all these different kind of mappings. Thank you all.